Midterm warm-ups. As we prepare for our midterm, we'll be reviewing many of the skills we've learned this semester. It's going to be extra important that you bring your notes packets on these review days. That means your chapters 1 through 5 notes packet and your 6-6 to 6-8 notes packet. We'll be seeing many of these skills in pretty creative ways. Like, take a look at this first section. See if you can pause and determine the value for n for 1, 2, and 3. As I look at number 1, I have the cube root of y squared equals y to the n, and I just want to figure out that n, that exponent value. Well, I know that I can rewrite the cube root of y squared as an exponent, like y to some sort of exponent. Power over root means I could rewrite this as y to the 2/3 power equals y to the n. Well, then it's clear to see that my n value matches up with that 2/3 because we have both sides with a common base of y raised to a power. So I know that n is going to need to be 2/3. Well, let's use this same logic on the next one. I have 1 over x to the 4th equals x to the n. So I just need to make both sides of the equal sign look like a base x raised to a power so I can match up that n power. Well, I can be a little creative here. I know that 1 over x to the 4th, if I move the x over 4th to the numerator, that would just be x to the -4 equals x to the n. Now my -4 and my n would be equivalent. N equals -4. Last time I'm going to try this strategy, but this time, look, my n is what the root is, the index on the root. So the nth root of 2 all to the 6th equals 4. Well, let's kind of try it like number 1. First, 2 to the 6 over n, power over root equals 4. Well, over here, I had that same base of y on each side, and that's why I could kind of focus up on my n. Here, I don't have that same base. I have a 2 and a 4. Can I force those to be the same? I know that 4 is really just 2 squared, so let's rewrite this as 2 to the 6 over n equals 2 to the 2nd. Okay, well now at least the bases match up, so I can focus up on those exponents. 6 divided by n equals 2. I know some of you are already going to know the answer right off. 6 divided by n equals 2. But let's try to find the answer algebraically. I'm going to put 2 over 1. If I have a fraction equals a fraction, I can cross multiply to find my answer. So that means I'm going to have n times 2, that's 2n, equals 6 times 1, well that's 6. Solve for n, and I'm going to get n equals 3. Interesting. Looking at this next example, we want to figure out some details about f of x. It wants to know on what interval the function is decreasing and what the endpoint of the graph would be. Let's take a closer look. F of x is a square root function, so let's remember what square roots look like. Y equals the square root of x is a graph with 3 pattern points back from 6-6 to 6-8. We have a point at 0, 0, one at 1, 1, and then over at 4, 2. Those are our pattern points for the parent function y equals square root x. The graph starts at 0, 0 and continues growing forever after that. We call that 0, 0 point the end point of the graph because it stops there. The rest of the graph continues to grow and grow and grow forever, not ending. This part of the graph is increasing across the entire domain of y equals the square root of x. Be sure you drew this graph in your warm-ups. So if I'm going to graph this new function to figure out these details I need to look for, I need to consider some transformations. A negative sign out front of the square root function is going to reflect my function about the x-axis. Then a -3 inside the square root is a translation to the right 3. Remember, inside, opposite. Okay, so let me draw my sketch. Instead of starting at 0, 0, now I'm going to translate to the right 3 and plot my end point. Then I would go over 1, up 1. Wait a minute, I'm reflected about the x-axis. So instead of going over 1, up 1, I'm going to go over 1, down 1, back to my endpoint, over 1, 2, 3, 4, and down 2. As I draw this sketch in, I can see that it is decreasing across the entire domain. So when I need to give the interval it's decreasing on, I kind of give it like I give the domain. It starts decreasing from 3 to infinity. Or I could say everywhere x is greater than or equal to 3, my graph is decreasing. The end point of my graph, well now since I have that stopping point at 0 or at 3, 0, I'm going to say my end point is 3, 0. Now that we've reviewed square roots, let's look at this next example. We have a radical function h with the following properties. A domain of x is greater than or equal to -2, and a range of y is greater than or equal to 4. We're also told that the function is increasing across the entire domain. So now we know that that means it's going to be a square root function that heads in that upward direction. We need to write an equation for h. Well, before I can really write an equation, I kind of need to picture what this looks like. I'm going to do this way over here. Okay, if I know the domain is x is greater than or equal to -2, I know -2 would be here, and my domain's going to be everything on this side of my x-axis. I can do the same thing with the range, 1, 2, 3, 4, and then it's everything above 4 on my y-axis. So these two places intersect right here. So that would be a good end point for my graph. And then I already know that it's increasing across the entire domain, so it would be headed up like this. Well, there is a quick square root function, and it looks like it's been shifted to the left 2 units, so translated left 2, and up 4 units. Well, I can write an equation for that. I know I'm going to have a square root function, and x plus 2 for left 2. And then on the outside of the square root, I'll have plus 4 for up 4. And there is my equation that meets those properties. Let's finish off by reviewing some inverses. Here we want to figure out if a graph's inverse is a function. So meaning, does it pass the vertical line test? Does every input map to exactly one output? There's a few ways we can do that. First of all, let's remember what an inverse is. That's when we swap the x and the y value and we solve for y to find the inverse function. So if I have the graph of the original, I could pick a few points on this graph and actually plot its inverse. So let's pull a few points off of this. I'm going to choose 1, 0, 2, 1, and 3, 0. Then I can just swap the x and y and plot those to have my graph of my inverse. So take a moment to plot. You're probably already leaning towards function or not a function, but take a moment to remember that the graph of an inverse is symmetric about that line, y equals x. So if I want to know if the inverse is a function, I'm going to focus in on my pink graph, my inverse, and just run the vertical line test. If I run a vertical line through right about there, I can totally see it's not going to pass the vertical line test, meaning every input doesn't map to exactly one output. That input of x matches to 2 different y's. So my inverse for this one is not a function. There's actually a quicker way to tell if my inverse of a graph is a function just by looking at the original graph. It's called the horizontal line test. If I go to my original function and run a horizontal line test across it, I can see that it would fail a horizontal line test. And because the original function fails the horizontal line test, the inverse, its inverse, would not be a function. So let's make sure we understand that. The vertical line test tells if a graph is a function. The horizontal line test tells if the inverse of a graph is a function. So looking at this second graph, if I run the vertical line test, I can see it would pass. So the original is a function. And if I run a horizontal line test, so straight across, yep, looks like we're good, then I can see that the inverse is also a function.